Yes, Shukran for the invitation. And it is an honor for me to have the chance to talk again here at this meeting. And I would like to present to you the results from a common research project, which is performed with partners from Germany, Egypt, and Jordan. And our focus is to recover water from mining industry, to use this as a new source for decreasing the freshwater demand and decrease the conflict regarding water reuse for industrial and civil application. And we just make an assumption to see how big is the potential for water saving in phosphate mining for industry. And we found an example for one mine, which loses about 3 million cubic meter of water per year. And besides this, it contains suspended solid amount, which contains about 85,000 tons of phosphate, which is lost with the discharge. So the idea of this project is to find and combine innovative and robust technologies in a lab at first case, and then in second to go further and demonstrate them at a site in Jordan at a phosphate mine under real operational conditions. The idea is to recover the water to ensure the water supply for industrial application and decrease the pressure for drinking water use. So the idea is to have technologies which can be applied and build up the knowledge together as equal partners in this project, and to cooperate and develop together and find solutions which can be applied later on and which are not only in theories but in practical as well. Partners are VDEh in Germany, Sarah Fieldtech, VDEh-Betriebs in Jordan, and research institutions as Jordan University of Science and Technology and the National Research Project in Egypt with Professor Heber. So the idea is at first we need for the application a removal of suspended solids, which is mandatory for any kind of water recovery. And for this issue, we use the ceramic flat sheet membranes from Sarah Fieldtech. The second step, this is a green box, is regarding water recovery. That means removing disturbing ions to fulfill the requirements from the treatment plant and use it at the mine again as washing water for all. And we have different approaches. I will go further in detail on the next slides. So one is ion exchange and the valorization of phosphate particles. Another is selective nanofiltration and membrane-based capacitive deionization, or the development of new membranes with metal organic compounds for improved membrane properties. All these things will be done in lab and finally go further and investigated at the site with support with the company VDEh-Betriebs from MN. So what we did is a sampling in a phosphate mine to find out what is the range of the water we have to deal with. The phosphate mine has a production about 0.5 million tons per year. And what we saw is that the water quality changes depending on the ore quality, which is mined. And we have a variation of the sulfate and the hardness content about factor 2 to 3. And further, we did a definition of the treatment aim, what is mandatory to use the water again. So first step for it all is the removal of the suspended solids. And for this case, we used ceramic flat sheet membranes, which were operated with under pressure. That means it is a very energy efficient system. It is very robust due to the use of ceramics. And we investigated different membranes, and finally we could filtrate and remove the particles with an under pressure less than 200 millibars with a flux of 200 liter per square meter an hour. And the turbidity of the permeate was 0.3 NTU. So what we did further is removing the particles. You can see on the right-hand side, which has a phosphate P2O5 content about 20 to 30% approximately. and developed a concept for the valorization again. What we did further is for the use of the membrane-based capacitive deionization, we need a previous selective removal of sulfate and calcium. And we investigated for that case a selective different membranes and determined one suitable, which we tested in lab. And the technical scale you can see on the middle. And we were able to approve the results from lab trials, reducing the sulfate content from more than 600 milligram to around about 6 milligram. That means over 99%. The chloride content was not decreased, but that was not the aim, because we want to remove this chloride content inside with the membrane-based capacitive deionization. So why we did these two steps? The idea is to have different concentrates which can be used further and valorized. Looking for sulfate, calcium sulfate as material, for instance, for the construction industry, or here if we are having a concentrate with chloride, then we can use it for the production of sodium hypochlorite as disinfectant, for instance. So what you can see here on the left-hand side, we have the original sample and the conductivity about 2,500 microsiemens, the chloride content over 400. Then we did the nanofiltration, which decreased the conductivity due to the removal of the sulfate. But still the chloride content with 360 is too high, because the requirement is stay below 240. So what we did is to find out what is the maximum desalting we can achieve. That means put as much as energy inside the MCDI, and we can decrease the chloride content from over 360 to 25 milligram per liter, and decrease the conductivity from 1,300 to 100. But the recovery was about 50%. But the requirements from the mine were not that high for the reuse. So that means slightly we adapted the parameters as desalting time, cleaning time, and flow rates. So finally, you can see we ended up with a water recovery of 75%. You can see on the right-hand side as optimization 3. And we decreased the chloride content to 220 milligram per liter, which is fulfilling the requirements of the sites for an internal reduce. So further on, another approach is to the development of new membranes. And this work was done by Professor Heber and her team. And the approach is to use metal organic particles and use them to improve the membrane properties as flux, strength, and fouling properties, for instance, copper or zinc, and then find out what is the best mixture of this together with different materials as polyvinyl chloride, cellulose acetate, for instance, or different solvent. You can see here, it's fluoride and pyrrole, for instance, and test them with synthetic waters to determine the best after performing simulations to decrease the amount of investigations that has to be done on a minimum by considering all the experience NRC has on this topic. So finally, it was tested with real waters, and you can see on the right-hand side the final composition, which was determined. So for the final test, we can see that the flux is about 30 liter per square meter an hour, and the recovery for chloride is in the range for 95 to 97%. So then, with this information and the final recipe, there was the production of DIN-A4 flat sheet membranes for further trials, and they were investigated with using the feed solutions, which were similar from the composition as the mining water we saw on the first slide. And what we saw is that there was an increase of the total TDS to the flux, but the flux is still about 17 to 30 liter per square meter hour, so that's fine. And on the right-hand side, there's the most important thing, that independent from the composition of the feed solution, we will fulfill the requirements of the mine to use this water again. The final approach we were investigating is the investigation from Jordan University, is to find out which resins are made possible to be used here. And we had different samples with chloride contents up to 890 milligram per liter, have been varying different parameters and ending up with the optimum conditions, finding the impact of the temperature, dwell time, and the resin mass. What we further saw is that there was a white precipitate when the resin was recovered, and the assumption is that it's based on sulfate. So now we had different approaches, and the reason why we are doing this different ways, for one question, is the water from each mine or further application will vary very strongly. And so we have the knowledge to say, okay, we have this water, then we use this combination, or we have this conditions at the site, then we will have another one. So what we will do is, the next step is to perform field trials. Here you can just see some pictures from equipment from BFI side with lab container and trail container. But on the right-hand side, you can see from Serafiltech the filtration plant, which is designed for 10 cubic meter per hour. And this will be the next step for October, November. It is planned to perform the trials in Jordan. We have been performing a visit of the site in May, and discussed details with the plant operators in Jordan. So when we sum up, we can say that the ceramic flat sheet membrane filtration is a suitable technology for the removal of the suspended solids. We have approaches for the valorization, and we find a combination in which we can treat the water that can be used later on as instead of fresh and groundwater. Outlook for the further work is the performance of benchmark trails with the NRC membrane and conventional membranes, do the field trials, and finally make an economic and environmental evaluation. And one of the very important steps is to just have not only a theoretical solution. For that reason, we have Irshad and Serafiltech in this project to make a concept for industrialization for a site, so that the results we can achieve will be shared between the universities to spread the knowledge we developed together as a team, as equal partners. And finally, to give the companies the chance to realize the solution to recover the water and put decrease the pressure regarding the subject. So I would like to thank you for your attention, and I would like to thank the team performing the work here all together with me and Professor Heber. I'm open for your questions. Thank you very much.